Thanks for the introduction. Hello everyone, I'm Kelita from Tsinghua University. Our work is analyzing the noise robustness of deep neural networks. This is a joint work with Mengchen, Shixia, Hangsu, and Junzhu. Today, deep neural networks have evolved to become state-of-the-art in a torrent of AI applications. Despite their promising performance, researchers found that there is a dark cloud over the building of deep learning. There exist adversarial examples that are intentionally designed to mislead a DNN into making incorrect predictions. In particular, DNNs are generally vulnerable to maliciously generated adversarial examples. This phenomenon brings high risk in applying DNNs to safety and security critical applications, such as driverless cars. In this work, we provide a visual analytics tool to explain why such a misclassification is made. There are two technical challenges. The first challenge is how to extract the data path of adversarial examples. A data path is critical neurons and their connections that are responsible for the predictions of an example. And based on it, experts can design more targeted defense approaches for DNNs. However, the neurons in a DNN have complex interactions with each other. Thus, it is technically demanding to disentangle these neurons from the whole network and thus form the data path. The second challenge is how to effectively illustrate the inner workings of adversarial examples based on the extracted data path. A typical DNN may contain hundreds of layers with millions of neurons in each layer. So there are too many neurons and connections to directly visualize an extracted data path. Directly visualizing all the neurons and their connections in a data path will lead to excessive visual clutter. To tackle these challenges, we have developed a visual analytics tool called AEVIS to explain the root cause of the wrong predictions introduced by adversarial examples. The tool has two parts: a data path extraction module to extract the critical neurons and their connections for the selected examples, and a data path visualization module to illustrate data paths in multiple levels. Now we use a case study to illustrate the basic idea of analyzing adversarial examples with our tool. We adopt a pre-trained ResNet 101 as a target model, which contained 101 parameterized layers. The normal images we used are from NIPS computation, and then we generate adversarial examples by the method proposed by the winning group of the NIPS computation. Our target model achieves a high accuracy on the normal images, but a very low accuracy on the generated adversarial examples. Next, I will introduce how an expert analyzes the root cause of a misclassification. In particular, the expert wanted to find the root cause why an adversarial panda image will be misclassified as a monkey by the target model. Firstly, to compare its data path with one of the corresponding normal example, he loaded adversarial images and corresponding normal images of the same class into our tool. At a layer level, we use dot plots to encode the activation similarity between these two data paths. Each dot represents a layer in this layer group. Then expert found that the dot is on the right at the bottom layer. It indicates the activations of this layer is similar between two data paths. And the similarity remained to be 1 until a deep layer. At the next convolutional layer, the activation similarity largely decreased. It means normal images and their corresponding adversarial examples diverge into different predictions. And the similarity continues decreasing to 0 in the following layers. Finally, resulted in the misclassification. To analyze which feature map is critical for the divergence, he zoomed into the feature map level visualization and examined the activation difference of each feature map in this Euler diagram. We use a number of stacked rectangles to encode the size of every feature map cluster. The average activation or average importance of each cluster is encoded with color. Here, this rectangle indicates that a feature map is critical for normal images, but not for adversarial examples. The expert checks the neurons, then examines the learned features in neuron level visualization. From the learned features and the activation heat maps, he found that the neurons learn to detect a black patch that resembles a panda's ear. This feature is critical for detecting a panda's face. To investigate the influence of this feature, he expanded the next layer. Then he checked the feature map that has the largest activation difference between two data paths. These neurons in the feature map learn to detect a panda's face. So it is critical for classifying a panda. And without detecting such a feature, the CNN fails to classify the adversarial images as panda images. However, the experts still don't know why the adversarial example is misclassified as a monkey. So the experts compared the adversarial example with a corresponding normal image and a set of normal monkey images. Triggered by the above analysis, he directly expanded the diverging layer to examine its feature maps. This time, the expert focused on the activations of the adversarial examples on the monkey's data path. Similarly, selected the feature map with the largest activation difference. The feature map learns to detect the face of a monkey. The behavior of the CNN is unexpected because there is no monkey face in the adversarial example. However, the adversarial panda image is misclassified as a monkey. To examine the root cause, the expert examined the detailed neural activations in this feature map and found that high activations appeared in the top right corner of the neurons. Comparing with the corresponding image patch, and examined the learned features of these neurons. The expert figured out the reason that a dark strip with a bright strip on each side is a recognizable feature for the face of a monkey. It makes the CNN mispredict the adversarial panda image as a monkey. Okay, after introducing the case study, now I want to talk about how the data paths are extracted and visualized. Data paths contains critical neurons and their connections that are responsible for the predictions of examples. So the key challenge of extracting a data path is to identify the critical neurons. A commonly used method is to select the most activated neurons, but this method may result in misleading results. For example, the figure shows the top 2 critical neurons found by such method for a sheepdog image. The most highly activated neuron learns to detect a baseball, while the second highly activated neuron learns to detect the head of a dog, which is indeed critical for classifying a sheepdog. This phenomenon is resulted by the complex interactions among neurons and the highly nonlinear functions that are used for generating the final prediction from activations of neurons. Therefore, the critical neurons in data paths are the neurons that highly contributed to the final prediction. In other words, we can keep the original predictions by only combining the contributions of the critical neurons. It can be formulated as a subset selection problem. The first term is to keep the original prediction, and the second term ensures to select and minimize the subset of neurons. As for a set of images, we minimize the sum of the difference in the predictions of the example set. Directly solving the subset selection problem is time-consuming because it is an NP-complete problem, and the search space is very large. So we combine a quadratic optimization with a divide and conquer method to find an accurate approximation in a smaller search space. To help experts explore the extracted data path, we design a multi-level data path visualization, which enables experts to analyze and compare data paths from high-level layers to detailed neural activations. At the layer level, we provide an overview of the extracted data path and guide experts in selecting a layer of interest. We first adopt the graph visualizer in TensorFlow, but we find for very deep CNNs, the visualization often suffers from a long skinny strip with a very high aspect ratio. And in our tool, we want to provide a compact overview with high-level statistical descriptions of each layer. So inspired by a segmented timeline, for example, a calendar, we segmented the network and generate a horizontal layout with a better aspect ratio. We formulate the segmentation problem as a pretty neatly problem to minimize empty space at the end of each line. But this method is not suitable for a CNN with building blocks that contained in state-of-the-art CNNs. So we add a regularization term for penalizing a segmentation scheme that cuts a building block into two parts. Because of the limited space for each node, we employ a dot plot as a visual hint to show the activation similarity of layers contained in this node to help experts detect the diverging point from hundreds of layers. With help of the layer-level visualization, an expert can detect a layer of interest and zoom into the layer to examine the critical feature maps in it. So the feature map level visualization should connect high-level layers and detailed neural activations. Here we focus on visualizing the shared feature maps between different data paths and the unique ones of each data path. Visualization of these belonging relationships are very useful for experts to understand the effect of these feature maps. Thus, the problem can be directly formulated as a set visualization problem. Among various such visualization techniques, we finally adopt compact rectangular Euler diagram because of its ability of depicting such relations and familiar to the experts and the ability of convening the number of feature maps. Besides, to reduce the visual clutter of too many feature maps, we cluster similar feature maps and use a series of stacked rectangles to represent a feature map cluster, and expand the cluster to inspect each feature map. After finding the feature map of interest, an expert can examine the neurons in the feature map in a separate neural panel. Following our previous work, we employ learned features and activations of the neurons to help experts understand the roles of the neurons for the prediction. In conclusion, we have presented a robustness-motivated visual analytics approach that helps experts understand the inner workings of adversarial examples and diagnose the root cause of incorrect predictions introduced by adversarial examples. The approach we proposed centers on the concept of data paths to tightly combine data path extraction and visualization. One interesting avenue for future work is to monitor the online testing process, detect potentially adversarial examples, and remove them from any further processing. The second one is to continue working with experts to conduct more experiments with the aim of designing more targeted and effective defense solutions based on the discovered root cause. Thirdly, another important direction is to analyze the robustness of other types of DNs, such as ions and deep generative models. Thank you. I'm happy to take questions.